In this video I present our work on privacy-preserving structure-from-motion. My name is Marcel Geffert and this is joint work with Victor Larsen, Pablo Speciale, Johannes Schönberger and Mark Boniface. Modern structure-from-motion systems are able to accurately and robustly reconstruct even large-scale scenes from noisy internet datasets. However, previous methods generally assume unrestricted access to all input data and complete control of the reconstruction process. Structure-from-motion gained a lot of attention since the reconstructed point clouds can also be used as maps to relocalize later on. This is well known in the research community, but now becomes also more prominent for consumer applications. New products like augmented and virtual reality devices need to accurately localize themselves in order to display information consistently over time and between multiple devices. Map-based localization for these devices is usually cloud-based. The device sends a processed image to a server and receives its pose. This involves an inherent privacy risk since images, even in processed form, can contain a lot of privacy concerning information that users don't want to share. Speciale and others approach this problem by introducing a privacy-preserving localization method. They replace standard feature key points with lines. The resulting constraints are sufficient to localize an image against a point map, but at the same time reliably hide image content that is not already present in the map. Still, their method requires a pre-built map. This is a significant limitation since maps deteriorate quickly and need to be constantly updated and adapted to changes in the environment. To overcome this limitation, we present the first full structure-from-motion pipeline to generate and update maps based on privacy-preserving line features. Our main contribution consists of a new relative pose estimation method from line features and 4 views with known gravity. Additionally, we combine existing solvers for pose estimation and point triangulation from line features with an adapted bundle adjustment into a full reconstruction pipeline. This allows a localization service to update and extend the map using available query images as crowdsourced data. The fundamental building block of our method is the line-to-point constraint. While a 2D key point in the image plane unprojects to an array in 3D space, a 2D line unprojects to a 3D plane. Here, the 2D line representation in the normalized image plane directly translates to the plane representation in 3D. For a perfect correspondence, the 3D point lies in this plane. Due to the additional degree of freedom along the line, a line-to-point correspondence only provides a single constraint, compared to 2 in the point-to-point case. Speciale and others use purely random line orientations when generating the features. In contrast, to enable our initialization strategy, we make a distinction between 2 different types of lines. We assume a known gravity direction for at least some of the images. This is a reasonable assumption in practice, as many devices already contain built-in inertial measurement units. For these images, we align a certain percentage of the generated lines with the gravity direction. For all other lines, we also assign random orientations. The gravity-aligned lines are only strictly required for the initialization, therefore a small number of overlapping images with known gravity is sufficient for our method. To initialize the reconstruction from an empty map, we need to estimate the relative poses between multiple images that can subsequently be used to triangulate the first points. In the case of line features, the minimal configuration requires 4 images. Estimating all poses in a single step would require at least 17 correspondences in all 4 images and is not feasible in practice. Instead, we propose a 2-step approach in which we can significantly simplify the problem by assuming known gravity directions. We start by finding feature tracks with only aligned features in all 4 views. We then align the image's y-axis with the gravity direction, eliminating the roll and pitch components of their poses. In combination with the aligned features, this enables us to temporarily ignore the height of the images and only consider their 2D poses. This is equivalent to estimating 2D image poses from one-dimensional images. In this setup, we can estimate the relative 2D poses for 3 images, triangulate the corresponding 2D points, and afterwards register the 4th image to these points. Since the roll and pitch component of the image poses can be extracted from the gravity direction, the only component left to estimate is the offset in this direction. We convert the problem back to 3D and estimate this offset from randomly aligned feature correspondences. Finally, we recover the image's roll and pitch and triangulate the 3D points. In contrast to key point-based SfM, Triangulation requires correspondences in at least 3 views. Additionally, the unprojected line correspondences and 3 views will always intersect in a point, independent of the image poses. This means that the point position can be estimated but not validated using only 3 views. Only with 4 correspondences we can compute an error between the triangulated point and the 4th view. Image pose estimation from 2D lines and 3D points was already presented by Special and others. This is done by aligning the planes of the backprojected lines with the corresponding 3D points. Since each correspondence only provides a single constraint instead of 2 in the case of key points, we require 6 correspondences to estimate the 6 degree of freedom image pose. To compute an error term during bundle adjustment, we project the 3D point onto the image plane and report the line reprojection error, which is the shortest distance between the feature line and the projected point. Collecting these error terms over all point observations, we jointly optimize the image poses and point positions. We assume all cameras to be already calibrated and therefore don't optimize any camera model parameters. We use multiple challenging internet image collection datasets to qualitatively compare the performance of our method with the standard SfM pipeline. While our method generally triangulates less points due to the additional required images, it is still able to reliably reconstruct even large scenes. Note that we are not able to color the point cloud since we don't have access to the image content. With our method, privacy concerning content like other people in the image is reliably hidden from feature inversion attacks. Only content that is consistently observed in multiple images and can therefore be triangulated can also be recovered. The shown images are feature inversions using the work of Peter Luger and others. They are generated from either the extracted image features for standard SfM or from projected 3D points in our line-based model. Our method is still just one more step towards fully privacy-preserving services. Limitations are both in the fundamental approach of line features as well as in our presented work. As the most severe restriction, we see the inability of the line features approach to project static content. The idea of privacy-preserving line features is built on the assumption that privacy concerning content is dynamic, but this is not always the case. Building a map of a private space such as a user's apartment will still reveal most of its appearance. The problem becomes even more significant if you consider high frame rate image sequences and videos instead of single images. Captured with multiple images in close succession, even some dynamic content might seem static in some images and would therefore not be protected anymore. An additional limitation of our presented system is the requirement for calibrated cameras. While it is sufficient to have the calibration available only on the device and not on the server, the absence of a full camera model limits the ability to handle inaccurate or changed calibrations. If you are interested in more information, including our code, please visit our project website and join our interactive sessions. If you are interested in privacy-preserving line clouds, there's also concurrent work on privacy-preserving visual SLAM by Shibuya and others presented here at ECCV. Their work focuses on real-time tracking and mapping with the line cloud map.